Hello guys, it's me again, Sir David here, discussing the continuation on the ACI direct design method and the ACI equivalent frame. So before I proceed with my discussion on the distribution of static moments, I'd like to give emphasis on how the frame strip is being created. Okay, so let's talk about the frame. So the frame is created on the basis of the extremities or the boundaries. So we have the boundaries of the mid uh, or the center half of uh, the center half of the transverse panels, okay, or the gate panel. Okay, so remember that if we have here now the columns in the longitudinal direction, uh, which is composed of a three span, your boundary is given in terms of these lines. No? So this dictates your boundary of your frame strip. Okay. So this boundary are actually what you call the mid center half or the mid half or the center half of the transverse panels at uh, uh, both sides of the column. Okay, this is the column, so this must be at both sides of the column. So this will dictate now the center line of the baby, no? the baby. Okay, on that side, and this is the center line of the baby that side. Okay, so this constitute now the extremities or boundaries of your frame strip or the equivalent frame. Okay, you may call it now the equivalent frame strip. Okay, while doing so, if you get 1/4 of this bay panel length, okay, so if I make use of of this line, which is L over 4, okay, okay, so this is simply uh, L2. This is the bay, this is the transverse direction, so this is L2 over 4 plus L2 over 4 is simply equal to L2 over 2. Okay? While these are, of course, your L1s, okay? So they may or may not be uh, the same in terms of dimension. Okay, so this one. Okay, so your L2 over 2, which is simply the sum of L2 over 4 on one side and L2 over 4 on the other side, will constitute your column strip. Okay, this is the column strip. So we have to bear in mind that these terms here are used now in the ACI code, so you must have to understand them very well, so that your parameters will be accurate, and when you put them into the formula we use in getting the percentages of moments. Okay, so this is your column strip, and the middle strip is simply what is the excess. Okay, so this is now your half middle strip here, another half middle strip here, so constitute the whole middle strip. So this is the half mid strip, and this is also the half mid strip. Okay, in short, guys, your section, your base section, or your frame strip section will now be defined in terms of this, no? So your frame strip section will be starting from the extremities, okay, which is composed of course the slab and the beam here, if there's a beam, and the column here, okay, column. So this part here are the boundary of your frame strip, which is of course again the center line of your page. Okay, so this is the column strip now will be one half of this and one half of this, which constitute L over 2 or L2 over 4. So this is now your column strip. Okay, so the rest here are simply the middle strip. Okay, so this is the half middle strip, and this is also half and the middle strip. So if the dimensions are not the same as to the adjacent bay and the adjacent length, then you have to take the average. Okay, so we are just simplifying uh, the computation based on the assumption that L1, L1, L1 here are the same, and L2 bay, the transverse direction, are also the same. Okay. So column strip, middle strip. So later on, this column strip here will be divided into a beam part and a slab part, no? Okay, so this will be divided into the beam part. Remember the projection that I told you, okay, and a small part here, which is the slab part. So the good thing about this um, alternate procedure on how to design a frame, including the slab, is that you may have now a feeling of how the moments are distributed at the columns, at the overhanging flange, and at the remaining slab here. Okay, which is a part of the column strip, and also the half mid strip that are existing on the two adjacent sides. Okay, so this is now the beam as defined previously in our first discussion, and this is now the slab. So remember what I told you, which is the slab and which is the beam. So this slab here and the beam here is a part of the column strip, and this half mid strip here are what? Not a part of the column strip. So they behave differently, but they contribute to the stiffness and resistance uh, given the static moment distribution that is used on the basis of what method you want. Is it the direct design method or is it the equivalent frame method? So that's how the frame strip is divided for you to be able to apply this table in your choice of methodology. Okay, so we're now ready to understand how it works. Okay, so for the static moment distribution, uh, which is a longitudinal distribution, these are just ACI coefficient. No? So this is not new to us. This is just a coefficient method. Of course, not the same as ACI method 1, 2, 3, but still, they are coefficient method. And you will notice that we have here a simple uh, a distribution on the basis of the type of span. What's the type of span? The type of span is an end span or exterior span. No? They're just the same. And if we are talking of exterior span, as I told you a while ago, then your moment diagram is not symmetrical. So it favors a little bit on the end support. Okay, the end support is smaller, has a smaller moment than the first interior support here. That's why if you will notice, the interior negative factor moments are bigger than the exterior negative moments rather. But the positive moments here, of course, are almost the same. Okay, so if we will consider later the positive moments. So these are uh, uh, the static moment distribution on the basis of what type of support do you have. Okay, so if the support is an exterior edge unrestrained, then for the interior negative factor moment, then 75% of your MO will be at this edge or at this support. Okay, interior support, and 0%, because this is unrestrained, is at the exterior support. The positive is 0.63. Okay, so if I will draw now, this is 0.75, this is or 0 rather, and this is 0.63. So this is for your case 1 scenario. Okay, so for your case 2 scenario, this is 70, 57, 16. So you just put here 70, 57, 16. Okay, so if this is my diagram, so this is just 70, 57, and 16. And so is true with the slab without beams between interior supports, meaning to say this is sort of a semi-flat plate, flat slab scenario wherein the beams are only at the perimeter of your building frame. Then without edge beam and with edge beams, there's a slight change, but a very small change in your positive and exterior negative moments. And for exterior, which is edge fully restrained, you will notice that this is the same as an interior support. Okay, this is a fixed scenario. Okay, fully restrained. So the moment diagram is just 65, 35, 65. 65%, 35%, and 65%. Okay, so that's how it is distributed. Okay, so this is a way of, kung wala kang software, kesa maghula-hula ka, if you are just designing a very simple structure, then this is perhaps a very good choice of procedure that you can depend on. You can risk your your uh, 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 what we, your decisions can take risk on giving decisions in terms of analysis and design. Okay, take note that the interior span, the total static moment shall be distributed as 65-35, 65-35, which is basically the same as this exterior edge fully restrained. Now, for column strip shall be proportioned to resist the following portions in percent of exterior negative factored moment. So we are now trying to, this is now the total, okay? This is now the total static moment here. From this, we have MO. We will now, what? Collect a portion of this MO to the column strip, and whatever remains will be given to both half middle strip. So this is now the use of this table here. And of course, if we are looking into the exterior negative moments or end, yes, exterior negative moments, factored moments is at the end span, we are talking of beta. Beta is actually the torsional factor, okay, something to do with torsion. And this end span has something to do with the fact that if you have here a a beam here, let's say this is interior span, the edges here are capable of resisting torsion. This is now the end beam na tinatawag, no? The end beam or the edge beam. Okay? So this edge beam will now dictate the torsional parameter beta. And of course, I have to compute L2 L1 and alpha 1 L2 L over L1 on the basis of our definition of alpha, which is simply ECID over ECIS. Okay? Okay, so what is B and what is S? B is the beam. B is the beam that is defined on this basis. Where's your beam? This is the beam. And your S, those are the two S, slab part. It's the beam part, that's the slab part. So if you want to get the moment of inertia of the beam and the moment of inertia of the slab, then we have to do it the old way, no? The old school. But if you want to make an approximate, I think IB can be approximated in terms of the I of the rectangular section, and just multiply a parameter in order to get the IB, so as not to involve yourself doing a lot of computation with regards to alpha. For beta t, okay, so there's a formula here for beta t that we are going to use both on the ACI direct design method and the ACI equivalent frame method. Okay, so that is how we can use this table, and another table here below is for positive. Remember that for positive, the effect of your torsional beams are not considered because you are looking at the mid span moments, and therefore there's no beta parameter here. Then you have only to compute L2 over L1 and alpha 1 L2 over L1 as your basis for these percentages. Of course, linear interpolations are necessary. Okay, so take note on these linear interpolations. So maybe in the problem set here, I will ask you to make a program on how to interpolate this linearly um, for your own use. Okay, so might as well do some programs on this for you to be able to use them later in your consultancy jobs. Okay, so for the transverse distribution of moments, all we need to compute are these three. Sorry, yes, three here, and take a look at the value of C here on the formula for beta t, where your C is also a torsional constant that has something to do with the dimensions of x and y. If it's a t-beam, okay, if it's a t-beam for your computation, You take note of x and y by on the basis of dividing this into small rectangles. Okay, so your x is always less than y. If this is bigger, then this is smaller, then this is x, that's y. This is x, that's y, and this is x, and this is y. Okay, if there's no edge beam, then you take the slab width equal to C1. What is the meaning of there's no edge beam? Huh? So if there's no edge beam, you have to uh, consider a torsional, okay, a torsional member wherein the width is equivalent to the column width. C1 is the column width. Okay, so what it means that if let's say you have here a column and you don't have a beam, so the slab is just straight like this. No? Therefore, this is your torsional member. This is your depth, the thickness of the slab, and the width is C1. Whatever is the column width will be the width of your torsional member here, if there's no beam. Of course, if there's a beam here, then you have to apply the concept of a beam part. You have to project it, no? So if there's a beam like this, there's a beam like that, then you have to consider the projection there. So this will be your torsional member. So there's no worry about it. But if there's no beam, you don't know how to project it, then the torsional part will simply be dictated by the thickness of the slab and the width of your column, which is C1. So if there's an edge beam, you have to define it on the basis of how I defined it on my previous lecture. Okay? Okay, column strip shall be proportioned to resist the following portions in the percent of interior negative factor moment. So this is just the same as the one 36.4.1 here. Okay, here's that. I think. Okay. I forget to place 36.4.1. So I just place it here. Okay, so this is for interior negative factor moments. So for interior negative factor moments, again, there's no beta t because there is no involvement of your torsional element. So from the table, beta t is automatically equal to 0 when the wall is a masonry, and beta t is equivalent to automatically greater than 2.5 if this is an RC wall monolithic with slab. Now, how do you distribute the column strips moment? Okay, so this is for the distribution of your column strip moment. So remember my drawing a while ago here, wherein this is the beam part, okay, and this is the column strip. Okay, so this is the column strip. Column strip. So the column strip is composed of the beam part and the slab part. So you have to divide in terms of percentages the column strip into the beam part, which is MB, and the remaining is equal to MCS minus MB. Okay, so your M at the slab now, if this is your MS, 1/2 of MS, this is your M of B, your MS is simply equal to MCS minus M. Whatever remains on this will be your MS of the slab. And you have to design it one by one. No? So the reinforcement for this is different, the reinforcement for this is different, the reinforcement for this is different. And this is the proportion. 85% if alpha L1 L2 over L1 is greater than 1, and 0 if alpha L1 or alpha 1 L2 over L1 is 0. Or it has a ratio equal to 0.85 alpha 1 L2 over L1 MCS if if it is in between these two, okay, provided that it cannot exceed, of course, 85% of MCS. So for the factored moments in the middle strip, then the formula is simply MO minus MCS is equal to MS. So whatever is the excess on the static moment, which is distributed longitudinally already, no? So this MO is no longer the full, so we better make it an M of the frame O, okay, minus MCS is MMS. So that portion of the negative and positive not resisted by the column shall be portion assigned to corresponding half middle strip. Multiplication of the negative positive factored moments by 10% shall be permitted. Okay, so you can modify it by 10% just like the redistribution approach. Okay, it shall be permitted provided the total time for a pan in the direction considered is not less than the static moment MO, which is equivalent to WUL2LN squared over 8. Okay, so that's the equation 13.3. Now for the additional formula to be used, no? So this is now to be used on the ACI equivalent frame method. In the equivalent frame method, this additional formula will now be added to this formula I just recently discussed, and that I will be discussing to you on my next video, so that you will not be mixed up and confused with so many restrictions and criteria. No? I know that this is very confusing at first, but if you master the art of applying this to many projects, to many consultation projects, you will be able to give your design reports and analysis as comprehensive and as justifiable, reliable as possible, based on both safety, serviceability, and economy, which is our main objective, main goal in designing building frames and structures. Thank you very much for listening. I'll see you on the next video.